So it's really my pleasure to give a talk and to be in this conference in honor of Elisha. So I will not repeat what has been said, but I completely agree with the description of Elisha, which was given by Alessandra just at the first talk. And I have to say that I had the office next door to Elisha's for 17 years with some discontinuities. And it's really a pleasure of every day to be one of his closest neighbor, and I hope that I will take advantage of him for the same amount of time. So let me now try to explain what we did. So usually I'm not doing any hyperbolic complex geometry. I'm doing more knot theory or related things, but it's kind of coincidence that for one time I have something which is related to complex hyperbolic geometry. And let me talk about this. So it's a joint work with Bertrand Deroin. And unfortunately, he is really on the geometric side of the story. So if you have technical questions, I suggest you ask Bertrand, who is not here. So I will try my goal is to first to introduce you about these Fibonacci TQFTs, because I suppose that you never heard about it. And there are very nice representations, nice combinatorial objects and representation of mapping class groups. And first I spend some time to explain how we can define such representations and to explain why we care about them. So first, the setting is the following. So we fix a surface S, a closed oriented of genus J, closed oriented, with some punctures, and P included in S is a set of numbered points x1, xn, a finite set of punctures. And I'm interested in representations of mapping class group of this surface. So let me denote it by mode of S and P. So it's usually the set of diffeomorphism from S to S, such that F restricted to P is the identity up to isotopy. So it's a very, very well-known and interesting group. And I will try to explain you in not more than 5 minutes how we can define interesting representation of this group. And I'm cheating because the explanation is just in this table, so in this blackboard here. So let me explain how it is defined. So we first consider K, which is a cyclotomic field, Q of Q. Q is the fifth root of unity, and everything I will do will be defined over this field. So it's a kind of basic field. And I make the following, let's call it A of SP. It's a very big space with a lot of relations. So A of SP is a free K vector space generated by some topological objects. So I'm not completely precise, but I hope that you will understand, by diagrams for graphs, finite graphs, embedded, too many D's, embedded in S minus P times 0, 1. So I really think that I have a surface which is a secant, so it's a three-dimensional object, and inside this secant surface there is a complicated graph which is embedded and not it himself. But this graph, I simplify the discussion, I project it on the surface, and I just see some diagrams. So the only thing I see for a diagram is a subspace of S which doesn't hit the boundary, the points, and what we see some crossings like this, some vertices for the graph, and we see some crossings like this one. Okay, and they are connected in some complicated way on the surface, and they do not they do not go through the marked point. and diagrams generated by, and here I forgot to say, isotopy classes of diagram. So I consider a diagram and I can move it along the surface. If I do not change the diagram, I consider it as the same object. And this very big space, I quotient it by a lot of relations. Yes? They can be triple intersection. Or even more. Okay? So I do not put any restriction on the number of incident edges at some point. And I take the quotient, so quotiented by local relations, which are shown here. Okay? Okay, so let me just give the name, because all of these relations are very, very famous for topologists. So this one is called the contraction deletion rule. So this means that once you find on a graph an edge, which has distinct endpoints, what you can do is you can do two things. You can contract it and you can remove it. Okay, so it gives you from one graph two other graphs. And I claim that in my space, A of SP, there is a relation between these three graphs. Okay? And the relation is the following. The graph is equal to the difference of the two, the contraction minus the deletion. So I add this relation for any time I see one edge somewhere. So a lot of relations. This is contraction deletion. This is called the fusion. So the fusion means once you find one 4-valent vertex somewhere, you just decide that this graph, which contains one 4-valent vertex, is equal to phi inverse of this graph plus phi inverse of this graph. And what is phi inverse? It's the inverse of the golden ratio. So phi is minus q inverse, but phi satisfies this relation. So this is why Fibonacci, that there is golden ratio somewhere. Okay? So this is the fusion relation. This relation says that once you find a crossing somewhere, you can replace the crossing with in two different ways by a simpler diagram without crossing. And the relation is that this equal to A times this one plus A inverse of this one. And this is also very famous. It's called the Kaufman Relation. And it explains that finally, well, all crossings can be expressed without crossings. You can remove them. And then there are 2 or 3 other relations. This is called the loop relation. If you have some loop somewhere in a graph, you can remove it, but you pay some price, which is phi. Okay? It just multiplies the graph by phi. If you have, sorry? Also, A is the square root of q, but I have to choose it, so I choose minus q cube. Okay? Because but the important thing is q is equal to a squared. Okay? But I can choose some specific root of q in the cyclotomic field, and I do it. So this is called the bridge relation. If I have a bridge somewhere, I think this is 0. And this is a special relation related to punctures. So you remember that there are punctures on the surface. So if you have one curve which goes around a puncture, you remove it and you pay a price. But this is not phi. This is the Galois conjugate of phi. Okay? 1 minus phi. So these relations are quite crazy. Okay? If you never see them before, you cannot really understand why they make sense. But at least I can give you the definition. Okay? So what happens? So there are a lot of interesting facts. The first one is that A of SP is finite dimensional. This is not very hard to prove. There are so many relations so that you can reduce any graph to a finite number of graphs. This is really something you can just check if you think of it 5 minutes. The non-trivial fact is that this is non-zero, okay? That A of SP doesn't reduce to nothing. Sorry? K over K, which is Q of Q. Okay? Wait a minute. Okay? wait a minute. This is easy to prove, this one. Something which is easy to prove is that A of SP is an algebra. And this is easy because you can just put one graph over the others using the crossings. So to define G1 times G2 as putting G1 above G2. Okay, you just put one over the other, and you find many crossings, and you decide that this is the product of G1 and G2, and you check that this is an associative algebra structure. Okay, this is not very hard to prove. What is also very simple to prove is that A of SP is a representation of mod SP. This is almost obvious because if you have a picture, or if you have a diagram on a surface and the diffeomorphism of the surface, you just apply F to your diagram, gives you another one. And because all the relations which I defined are local, or happens in small disks, it's obvious that this gives you a relation. So if I write a picture, I put F of the class of G is the class of F of G. So it's really obvious, okay? A representation of a mapping class group. Another fact which is interesting is that A of SP has some involution, has an anti-involution, which is just given by mirror image. So if you have a picture, you just change all the crossings. So it's anti-involution, takes a mirror image. Image of G, and simultaneously, if you have some scalars, you have to replace Q by Q inverse. Okay? And so it sends X, G to X bar, G bar. So what is X bar? Where Q bar is Q inverse, so maybe you know that this defines an evolution of the cyclotomic field. And G bar is just the mirror image of G. Just change all the crossings. And it's easy to check that you have this respects the product. So it's anti-involution. So all these are easy to prove, and there is something which is not easy to prove, which I will not. So let me add this here, the theorem. Is that, well, it's non-trivial. So A of SP is isomorphic as an algebra to some very simple algebra, which is just a matrix algebra. Just M to some D of K. Okay? And this is not easy to prove, but it's not, well, it takes 1 hour maybe to prove it, okay, with all the details. So how do I define the Fibonacci representation from that? So now there is a trick. So I recall that here is the group mod of SP acts on this algebra here. So if you believe me that these two algebras are isomorphic, this gives you an action of mod of SP on this matrix algebra. And here there is a very famous theorem of algebra, which is an automorphism of a matrix algebra is just a conjugation. Okay, this is the Skolem-Noether theorem. Any automorphism is conjugation by something. So what it means, it means that F acting on X, so X is an element here or an element here, is a conjugation by some matrix, is rho of F, X, rho of F inverse. Okay, for some. And rho, what is rho? Rho is a representation from mod of SP into, so it's a conjugate, it's a matrix which conjugates. So this is defined up to a scalar. Okay, you have the same conjugation by multiplying. So it's a representation in the projective in PGLD of K. And this is a Fibonacci representation. Okay? So it gives you, for any S and P, a projective representation of the mapping class group. And it's computable. Okay? So maybe I use more than 5 minutes, but this is one way of explaining why this representation exists. So let me now give a list of properties which are very important for us. So let me give a list of properties. So there is one very important property, maybe the first one. Well, because of this, it's constructed using a fifth root of unity. You will find it. So if you take for any gamma simple curve, if you take T gamma, so T gamma is a Dehn twist, okay? There is a very famous, the simplest element in the mapping class group is just a Dehn twist over a simple curve. This has order 5, okay? And this is because you used a fifth root of unity, and this is where there is a similar construction for any, you replace 5 by what you want, okay? But here it's 5. Second property, so this is very important. Rho is irreducible for any SP. So any SP, maybe I will replace it by Gn, okay? So it only depends on G, the genus of the surface, and the number of Marx points. So rho is irreducible, and it's even Zariski dense representation. Okay, so next property. So because of the anti-involution, which is something which you may notice, maybe you know that in a matrix algebra, if you have some anti-involution, there is a dictionary, it corresponds to a Hermitian form. So it's adjunction with respect to the Hermitian form. So the anti-involution is the adjunction with respect to some h from k to the d to k, which is a Hermitian form defined over k. So it means that the representation, indeed, rho is a representation mod SP into PU of H. Okay, it's a representation which preserves a Hermitian form. So now you start liking this complex hyperbolic geometry, which is arriving. Yes. Sorry. There is no problem. Yes. Yes, it's a really group which is Zariski dense. This group is Zariski dense in PGLD of C. Okay, maybe Zariski dense when you embed K into C. Maybe this is what annoys you. Maybe. Sorry. The norm is a product. The signature of your Hermitian. Okay, I will give you formula for the signature. It's not your question. Yes, but what it means, I know Hermitian. Yes. Indeed, there is a Hermitian form defined over K, but I will embed K into C, and I will give you the formula. So, but it makes sense for this. So there is something which I will not say. So rho preserve a lattice. I mean Z over Q to the D included in K to the D. So this means there is a preserved lattice. I will not tell any more about it, but it means that everything I'm talking about is arithmetic. Okay, so all complex hyperbolic manifold I construct are arithmetic. I don't give any more detail, but we are really inside the arithmetic world. Okay, but I will not give more detail about it. And next, I can give you what you want, the dimension. Okay. So the dimension D, so D I call it dGn, okay, because it depends on G and N. There is a nice formula. Let me write it in a fancy way, but which I like. This way, phi to the N, 2 plus phi to the G minus 1. So phi is a golden ratio, I call you. And this is an algebraic integer here, okay? Phi to the n, 2 plus phi to the g minus 1. So this is an element in Q of phi. And we take the trace. The trace, it means the trace of the multiplication by this element in this field. Okay. And here you can find a lot of Fibonacci sequences everywhere. Okay, if you try to understand what means this formula, and the last property. Well, you have 4 ways of embedding k into C. Okay, because you have 4 fifth root of unity. So let me make a picture. So 1 is not a fifth root of unity. Okay. So here are the fifth root of unity. If you take conjugated roots, you find completely similar series. So I'm interested only in these 2. Okay. And if you take this one, so if you take q equal to e to the I pi over 5, you really get a Hermitian. So you get some representation, rho, from mod SP into some PU, PQ. Interesting representations like this. If you take the other one, no, it's another Q, okay? So if you look at it, it's really slightly different. If you take the other root, you get something which is unitary. It's PU of D. Okay, so you have 2 embeddings, and one is unitary, and the other one is pseudo-unitary. And this is not interesting for us. Okay, so from now I suppose that I take this root, the simplest root. So this representation gets into PU of PQ. Okay, and I can give you the signature, and the signature, let me write it here, sigma Gn, which is okay, P minus Q, and the signature depends on G and N, and the formula is the following. I like this formula. J to the N, 2 plus J to the G minus 1. So now J is a third root of unity. So J satisfied J squared plus J plus 1 is equal to 0. So in some sense, it's exactly the same formula, but you replace the golden ratio, pi, by the third root of unity. Okay? So it's the signature. So it's strange, but I've written here a table. So here is a table for P and Q. Okay? So here is G and N, so you can look at it. For any values of G and N, you can find, I wrote you P and Q. Okay, so the signature of the Hermitian form. And you see that there are a lot of Fibonacci sequences everywhere, but I take some time to find them. Yes, but this is what I'm saying now. So the picture in orange corresponds to complex hyperbolic structures. Okay, no. Well, no, complex hyperbolic structures on moduli spaces. Of course, well, you see here there is a 4-1, so it means that you have some hyperbolic geometry here, but it doesn't go into my story. Okay. No. So what is the aim now? So what you see is that this will increase a lot. Okay. Here you have 20. It's already too big for whatever we want. But what's the purpose of my talk? So what's the aim or the motivation? Is to try to see if these representations, call them rho Gn. So these representations are representation of the mapping class group mod SGN into PU, PQ, okay, are holonomies of geometric structures. So I will. So it means here I want to think of this group as a group of isometry of some space, which is modeled on the symmetric space. And here I want to think of this group as a fundamental group of some manifold. And let me explain this. So first, PU, PQ is an isometry group of some space which I call HPQ, which is the symmetric space of PU, PQ, and you can think of it as a space of decomposition of, say, E plus E minus. So you take your complex space with the standard Hermitian form, P and Q, and you decompose it as a sum of two subspaces. One is positive. So the restriction here of the Hermitian form H restricted to E plus is positive, and H restricted to E minus is negative, and E plus is orthogonal to E minus. So if you think of the space of all such decompositions, it's a Hermitian, it's a symmetric space, and this corresponds to a geometry, and it's more complicated to think of what has to be put here in mod SGN. So now I will have to say something which is more difficult to explain. I will try. So what for a mod of SGN? So mod of SGN is a fundamental group of some space, which is well known. So mod SGN is a pi1 of some space which is called MGN. And MGN is a moduli space of curves. So MGN is just a space of pairs C and X1 and Xn. And now C is not just a topological surface, but a complex surface. So where C is a Riemann surface, and X1 or Xi are points inside, and I consider this space up to biholomorphism. So this is a finite, this is a 3G minus 3 plus n dimensional complex, and I would like to say manifold, but it's not, okay, orbifold. So I will not get really into these details, which are very annoying, but just think it's like a manifold, okay? So you have some points where there is some isotropy here. And this is, of course, very important. And when I call the pi1 here, it's pi1 in the orbifold sense, okay? So all this you may know. Triangle groups are examples of such kind of problems. So maybe we would like to say, can we find a geometric structure on MGN, which is modeled on HPQ, such that rho is a holonomy of this geometric structure? Okay, so that's a question. That's a motivation. So for this to happen, at least for a Fibonacci representation, we need at least that the dimensions are the same. Okay, so for that, we need that 3G minus 3 plus n is equal to the dimension of HPQ. And this dimension is P times Q. Okay? So if you look at this table and you want to see when the product of these two numbers is equal to 3G minus 3 plus n, okay, I give you the answer. You find exactly the orange, these 5 examples here. Okay? And and the problem we face here is that the MGN is not a compact space, so we have to compactify it before we find a geometric structure. So let me explain this very roughly. So first we define mod Gn. I put a 5 here, and 5 means that I kill all fifth power of all den twists. So it's a quotient of mod of SGN by the group generated by the fifth power of all den twists for all gammas. Okay, for all gammas. And just because of the main property of the representation rho is indeed the representation of this quotient here to PU, PQ, okay? Because it has this property of sending all the fifth power of den twist to the identity. And this group here corresponds to a pi1 of some compactification of the mapping class group. So let me explain this in 1 minute. So there exists a well-known, not for me, but and maybe not for you, but well-known for many people, compactification of MGN called, so we already heard about it in Vincent's talk, noted MGN bar, and it's called the Deligny-Mumford. Maybe sometimes Knudsen is added. I don't exactly know Mumford compactification. And it consists in adding to a Riemann surface a stable Riemann surface as a set. MGN bar is a set of stable curves, which means nodal surfaces. So surface with some singularities. So let me give you an example. You can glue two torus here along one point, and this is not a smooth Riemann surface, but it's some point that you add to compactify your space. And if I make a silly picture of the moduli space here, so this is MGN bar. So MGN bar is compact, and what you get at the boundary is a union of what we call divisors, but these divisors correspond, there are a finite number of them, that corresponds to all the possible stable curves you can add. So for instance, here you have this stable curve, which consists in adding some elliptic curve here, and it corresponds to a hypersurface, and this is the picture. And the picture is such that if you take an element in the pi1 which goes around here, if you take a small element in the pi1 which goes around this point, this divisor, this gives an element in the pi1 of MGN. Okay, and if you go around here, you will find T gamma, so the monodromy, the loop which corresponds to going around a divisor at infinity, is exactly the den twist which corresponds to the curve which has been pinched here. Okay? So recall that at the beginning I had a curve of genus 3 here, and to get this I pinch this curve gamma. I just pinch to one point. And this corresponds to some specific element in the mapping class group here, which is T gamma, and it's exactly the correspondence here between den twist and this picture of MGN bar. So what I do now, so there exists some space which is called MGN bar 5. What I do here is I do some very standard construction in algebraic geometry. I put some ramification here at all these boundary divisors. You can think that you add some conical angle here of order 2 pi over 5. If you think geometrically, you just change the structure here so that you have some ramification of order 5 along all these boundary divisors. And this can be done, and I don't have time to give the details, it's very long, consisting of, with ramification of order 5 along all boundary divisors. So there is one way to do this construction I don't explain more. And the property is that it's pi1 of MGN bar 5 is exactly this mod GN5. Okay, so it's one geometrical way of producing this group, mod GN5. And because I do not really change the underlying space, it's exactly the space of stable curves, but where I change some ramification, indeed the cohomology of this space, MGN bar 5, with rational coefficient is the same as the cohomology here of MGN bar without the 5. So it's a trick which changes the group but doesn't change the cohomology of the space. So now I can state some theorem. Let me keep this here. So the theorem, there are two parts. First one is somewhat technical, but it's fundamental to explain the second one. So there exists a smooth orbifold compactification. I call it MGN bar E, and explain which is obtained from MGN bar 5 by contracting, I explain in 1 second, contracting elliptic tails. So this is technical, but it's very important that it's not exactly this compactification I will use. Among all these divisors, there is one specific one, which is this one. So this is an elliptic tail. It's some stable curve, which is obtained by just adding an elliptic curve without marked points. Okay? And what I do is that this corresponds to some hypersurface here, and I just blow down it. So when you make a blow down, you know that in general you have something which is not smooth, and we claim that we can contract all these elliptic tails, and it gives a smooth orbifold. Okay, so this is one part of the theorem. Sorry? Yes. There are some stability assumptions. Of course, there are. What I do, I identify all these of the curves which correspond to the same elliptic tail. So this is a contraction, and it gives a smooth. Variety. And the second one is that for Gn in the list which is written here, so 0, 4, 0, 5, 1, 2, 1, 3, and 2, 1, all the cases which are written here, there exists the representation rho Gn, which is from pi 1 of mgn e. So this compactification into PU, PQ, where P and Q are exactly like in the table, is the holonomy of a complex hyperbolic structure. So is the holonomy of a complex hyperbolic structure on this space. And nothing else, okay? So exactly this space, which has a complex hyperbolic structure. So it gives interesting new examples of complex hyperbolic structures on moduli space. And let me comment the cases which are written here. So most of them are well known. So here you have M04, and M04 is pi 1. It's indeed a triangular group 5, 5, 5. So it's just a triangle with 3 singular points of order 5. And this is a well-known example of hyperbolic triangle group in dimension 1. So this is a kind of very simple example. Okay? If you take this one here, you find a complex hyperbolic structure on moduli space of P1 with 5 points, with a ramification of order 5, something which are well known in this place. Okay? This is a Hirzebruch surface. So, of course, we do not discover a new complex hyperbolic surface, but what we say is that the representation, which I explained at the beginning, is the holonomy of this surface. So this is something interesting. Of course. They are all arithmetic by construction. So these are, nice examples. So here you have this 1, 2, and this is something which appears in a Livney thesis. Okay, so there is an example which was really produced by Livney, and this is exactly the one we obtained here. Okay, and we have 2 other examples which seems not to be known. Yes. Sorry? This one? Because, well, it's trivial. It's a point. The symmetric space is just 1 point. And M03 is 1 point. So I could add it, but it would be, you have a complex, interesting structure on the point. Okay. So this example was well known, and this Leibniz thesis, and these two are seems to be new. So this is a 3-dimensional example, and this is a 4-dimensional example. And let me give some interesting applications. So it seems that what we can add, maybe I can put it as a third part. There is a map from M13E to M12E, which just sends it's called a forgetting map. So you can just send a curve with 3 points to a curve with the first 2 points. Just forget about the third point. And this is holomorphic. So it seems that this was not known. An example of a holomorphic map between complex hyperbolic varieties of higher dimension, of dimension more than 1. Okay, so here you have a map here from a 3-dimensional complex hyperbolic manifold to a 2-dimensional one, which is non-trivial. So it seems that it was a question by Hsu. And maybe Martin already thought about it, no? No? Well.
Is it covering?
No. I don't exactly know. I can tell you what is the pi1 of fiber, but I don't know. But this is well, what are the fibers? It corresponds to a genus 1 curve with 2 points, which are order 5. Okay. So well, that's kind of motivations. How much time do I have? 15 minutes. Okay. And let me now explain how we can prove this. Well, I will not give you a proof, but at least the proof of the point number 2, which is maybe the most interesting, is a combination of the proof of 2. It's a combination of two tools. One is very well known and is really the specialty of Bertrand, so don't ask me more questions. It's a theorem of Hsu for finding holomorphic equivariant maps. So you have this MGN bar E. You try to define a map F from the universal cover of it to HPQ. So there exists an equivariant map from the universal cover here to this symmetric space, which is equivariant with respect to the rho Gn. This is easy to construct, and the point is that you try to find a harmonic representant, and then you apply a lot of complicated theorem, which tells you at the end that F is holomorphic. And if you have some extra information, you find that F is exactly the holonomy, the developing map of some holomorphic structure. And this I don't explain, but it's a very technical and standard thing. And the other, I said it's a combination, so this is the first thing. And the other one is the computation of a Toledo invariant. Say tau Gn, which is indeed some element in H2 of MGN bar E, but as I told you, this is the same as H2 of MGN bar Q. Okay? And I would like to explain what is this Toledo invariant and how it can be computed, and it is really the heart of our paper. Okay? And there is what is very nice is that this Toledo invariant has a lot of interesting properties, which allows to compute it, but I find it interesting by itself to think about this. So let me make a kind of crash course on Toledo invariance. So instead of explaining you correctly one version, I will explain it very quickly, 3 ways of thinking about Toledo invariance. But I have some reasons for that. So, so there are at least three independent definitions. So first, I suppose that I have any representation from the pi1 of any topological space, so it's very general, into some group like PU, PQ. Okay? So it's in this kind of generality, I claim that there is a Toledo invariant, tau of rho, which is some class in H2 of X with rational coefficients. So how is it defined? Well, this is really the way I understand it, so that's why I want to explain. And this is at the same time the way I compute it. So maybe it's not the most geometrical way, but at least it's very computable. So once you have such a group PU, PQ, this group is not simply connected. So it has a universal cover. And the pi1 of PU, PQ is something easy to compute. It's Z2 divided by PQZ. Okay, so let me skip the explanation of this. So it has some Z part and some finite group part. I send this in Q. And I make an explicit formula here. So phi of xy is equal to 2 qx minus py divided by p plus q. So it's one way to transform this group into the rational numbers, which it's very important to take this one to have good formulas. And once you have done this, you can apply a kind of obstruction theory, which is a big word for something which is not so complicated. So there is an exact sequence which corresponds to this P1 of PU, PQ, which is exactly the center of the universal cover here, PU, PQ tilde. So this is the universal cover of PU, PQ into PU, PQ. And you have a representation here from pi1 of X to this space. And the question is, can you extend this representation to the universal cover of PU, PQ? And you try. So you take any kind of section, and you check if your section is indeed a group morphism, and in general it is not. And the fact checking that it's not exactly gives you the obstruction here of rho, an element in H2 of this group here, pi1 of X with coefficient in this pi1 of PU, PQ. So this is a very complicated thing, but this you can replace it with Q, applying phi, and there is a comparison map between the H2 of the pi1 and H2 of X, and so this you can send it to H2 of X with coefficient in Q. Okay, so I call it phi of obstruction of rho, and this is one way of defining a Toledo invariant. One way. Let me do another way. I go very quickly. Well, you have this. There exists an equivalent map F here from the universal cover of X to PU, PQ to the symmetric space here. Well, I put it above. Because HPQ is contractible, you can find such a smooth map here. And on HPQ, there is a Keller form. Omega is a Keller form. So this is a kind of way of defining which Vincent likes, and Pascal, and a lot of people here. And Keller form on HPQ. And this is a rho equivariant map. And what you do is you pull back the Keller form by omega. And because the map is equivariant, this pullback form is a form on X. And this exactly is the Toledo invariant. So F star omega is, say, pi star of some tau where tau is in the H2 of X, say in real coefficients. In de Rham, it's a de Rham representative of the same class. Okay, so it's another way, which is, for geometric reason, is really the key. It explains why Toledo invariant controls the fact that you have a holonomy representation. Okay, so this is why I explain in this case here. And there is a third way, which I like a lot because it gives, in some sense, a full invariant. I have 5 minutes. So suppose that, so here I cheat a little. I suppose that my representation is linearized. I mean, it's not in PU, PQ, but it's in U, PQ. So I don't want to explain what we do if it is not, okay? So don't ask this. But this is a nice construction. Suppose that your representation takes values in UPQ. Okay? UPQ is a unitary group of some space, which is a Hermitian space of signature PQ. It acts linearly on CPQ. So you can, if you have a representation, you can form a bundle, a flat bundle, corresponding to this representation. So this corresponds to a flat bundle. E, call it E rho, which is just the universal cover of X multiplied by C PQ divided by pi1 of X. Okay, and the action is diagonal here. You act simultaneously on both factors. This gives you a flat bundle. And the flat is a flat Hermitian bundle. So in each fiber, you have a Hermitian structure. And what you can find is the decomposition of this bundle is the sum of two bundles, like in a symmetric space. So you can split. There exists a splitting. E rho is equal to E plus E minus, but it's a splitting of bundles. And this is positive part and negative part. And once you do that, this bundle is flat, but some bundles are not flat. If they were flat, it would exactly explain that the Toledo invariant is 0. So the Toledo invariant, in some sense, measures the non-flatness of these subbundles. And let me define this generalized invariant. So we define, with Bertrand, we call it SCH, you will see why, of rho, is the following thing you take. So for people who know, it's a Chern character of E plus minus the Chern character of E minus. So this is a full characteristic class. It's a combination of Chern class, but in different ways, organized in a different way. And it is a series of cohomological classes in X. I don't have time to explain what is the Chern character, but Chern character of bundle at 0 degree is just the dimension of this bundle. What I claim is that if you look at the zeros part of this expression, it's just P minus Q. So this is the signature here. Okay? And if you take, this corresponds to the degree 0 part. And the Chern classes have even order, so you have elements in H0, in H2, H4, etc. And the second one is exactly the Toledo invariant here. Toledo invariant of rho is a degree 1. It's a Toledo invariant. Degree 2, sorry. And you have some extras, you have an infinite number of other classes, which are interesting. So what I would like to do, and I'm not able to do, is not only to compute the Toledo invariant, but to compute all these invariants. And all these classes are in the cohomology class of, think that X is MGN bar. Okay? So cohomology of MGN bar is another topic that is very well known, but not by us. Okay? So in particular, H2 is something very explicitly known. So I can just say that one of the main theorems which allows at least the computation of the Toledo invariant is the fact that the data of SCH of rho Gn for all Gn. So these are families of cohomology classes in MG n bar are related themselves. Okay? So when you go from MGN to other values of G and N, they are not independent at all. So there are a lot of relations, which finally gives you that to compute all of them, it's sufficient to have a finite number of information. And this is encoded in some structure which is very interesting, which is called Cohomological Field Theory. So clearly I don't have time to explain what is a cohomological field theory, but this is a lot of information, but at first it's an algebra V, which is called a Frobenius algebra. And Frobenius algebra, you saw what are these Frobenius algebra in the examples I gave you. So in the case, I had two cases. The first one was Q of phi. So I had to say that this cohomological field theory depends on Q. So anytime you give me one root of unity, so example of order 5, which I gave at the beginning, but there are Frobenius algebra for any root of unity. There is an algebra which happens to be a number field, but I'm not able to prove it. And in the case of the fifth root of unity, you had two examples, the unitary and the pseudo-unitary series. The Frobenius algebra was Q of phi in the unitary case and Q of j in the non-unitary case. So the formula I gave you for the signature are indeed completely explainable by this Frobenius algebra. Okay? So the Frobenius algebra, it's an algebra plus something else. I don't have time to explain, which is not very complicated, but anyway. Gives exactly the formula for the signature. Okay? And you have this an extra thing, which is the R matrix. So I'm very, I know a lot of R matrices because I'm doing knot theory, but unfortunately it's completely different from the R matrices I know. It's the same name for a very different object. But if you know the R matrix, you can compute all the Toledo invariants. Okay? And the R matrix is some endomorphism of V. Okay? It's just a matrix which acts on this Q of phi of Qj. And just give you an example and I stop. For the example of Fibonacci, the R matrix is the following. So indeed it's, well, let me cheat. Okay, I simplify a little for this. The R matrix has a very strange expression, which is 1 over 2 17ths, 23, 10, minus 23. Let me check this formula. Oh, yes, correct. Okay, I have some luck. I just claimed this computation took us 1 month of checking because we didn't believe this formula was correct. But I claim that I don't have time to explain, but just this matrix and this algebra here gives you an explicit formula for the Toledo invariant for any G and N. Okay? And there I have a formula for which only depends on this matrix. And we use these formulas, and we prove that the Toledo invariant is maximal for some. So indeed, something I forgot to say that in the Hsu theorem, what you need to apply the thing is that the Toledo invariant, if you know that the Toledo invariant is equal to 2 divided by p plus q times the first chain class of the canonical bundle, then you get the holonomy structure. So this is something we can ask Vincent or Pascal. So at some point you need to compare the Toledo invariant to the canonical bundle of the MGN-E. And if you can prove that this formula holds, then you have this. So finally everything reduces to a comparison of two classes in H2 of MGN bar. And as we have this strange formula here, we can do the computation and check that it works in all these 5 cases. So that's a strategy. It's computation. I don't have more than this to say, so let me stop now. I'm out of time.